So in today's lecture, the basic mistake that we were committing was in terms of the phase difference that I took between the voltage and current of the output. So in fact, if we have a quick recap of things that we have studied in the past, so the waveforms shown over here are corresponding to the different loads. For example, for a resistive load, the I and R, the current voltage, they are always in phase. But if we have inductive load, then current will be lagging the voltage as shown. While for capacitive load, the current will be leading the voltage. Now, for the RL circuit, so what happens in this combination of RL is that the voltage which is supplied to RL and the current through this load will be having a phasor as shown here. So current will be lagging voltage by a certain angle, let's say phi, and that the value of phi depends upon the value of inductance and resistance. So higher value of inductor will make phi large, which means that the current will be lagging voltage by more angle. And this was something that we could not employ in this case, because in fact what we did in equation B is, so this equation A is correct. So let me write this for you. So this was correct, this was correct, and then we finally talked about the current in terms of forced and natural response was correct. The mistake that we did was that force response IF was taken as Im sine omega t minus alpha, assuming that the current IF will be lagging the voltage across the load by alpha. So this is not the case. In fact, the ISER, this current, lags the supply voltage by angle alpha, the firing angle. But we should have taken this angle, the angle between V naught and ISER, because we are interested to draw the phasors between RL, load RL, voltage of RL, and current through RL. This will give us the correct angle. So this should not be taken as alpha, rather let us assume and take this angle as phi. So phi represents the angle between V naught and ISER, the current through it. So this is the basic mistake that we committed, and the equation that we approach to was wrong. So let's correct this all. This is phi, and then again, now again we took I alpha as 0, and in fact while solving to differential equation, the constant a is a constant, not a variable, so it shouldn't be dependent on time, rather it should be it is always a constant, and thus this a can only be evaluated when we substitute. Let's correct this first. This is phi that we just took, and omega t will be substituted as alpha. So since we are talking about the initial conditions where omega t is taken as alpha, so it should be taken as alpha. And then we have, if we write t in terms of, so alpha, this can be written as, so let me write this as e raised to the power, since alpha is equal to omega t, and from that we get t as alpha by omega tau. So we can write this here as alpha is equal to omega t, and this will give us t equal to alpha by omega, and we substitute this here. Now we further substitute a in equation B. So the corrections again employed are Vm by z sine omega t minus phi minus Vm by z sine omega t. Okay, this is minus Vm by z from a sine alpha. This is alpha, and this is phi. Then another term e raised to power alpha by omega t into e raised to power minus t by tau, e raised to power minus t by tau. So we further simplify this. We take Vm by z as common, and this can be written as sine omega t minus phi minus sine alpha minus phi into e raised to the power alpha minus omega t divided by omega tau. So this is the required expression for current, instantaneous current I, and this current of course is the current that lies between. So this relation holds for omega t lying between the extension angle and the firing angle alpha. So this is the required equation, and I hope that explains.